Hello student, in this lecture we will study about electromagnetic waves, and this is our first lecture in electromagnetic wave series. So we begin this electromagnetic waves with the topic of displacement current. So first of all, let us study what is this displacement current. Because we want to study about electromagnetic waves, so all these electromagnetic waves, the concept was given by a scientist which we call as Maxwell. So Maxwell is the name of the scientist which introduced electromagnetic waves, and Maxwell also gave the concept of displacement current. So Maxwell first of all showed that a changing electric field, if there is an electric field E and it is changing or it is varying, it also produces a magnetic field that we have studied in our unit of magnetic induction and all the previous unit, that whenever there is an electric field, it creates a magnetic field. And whenever we study magnetic field, we study Ampere's circuital law. So what is Ampere's circuital law? We can define Ampere's circuital law. It is simply the line integration of magnetic field B dl. This shows the surface integration. If it is dl, then we call it as a line integral over a closed surface. This is equal to mu naught times of the current which is flowing, which is varying with time t. So this is our simple Ampere's circuital law, that V dot dl is equal to mu naught I, and here I is a function of t. So from here we can say that our electric current I is a function of time. And simply in physics, we can write down the current I is equal to dq upon dt, that is the change in the charge with respect to time. So in order to study this current which is time dependent, we simply take a parallel plate capacitor. So this is a parallel plate capacitor. We can say that here the charge may be positive and here it may be negative. So this is how we can denote a parallel plate capacitor, and through which the current I is flowing. So if we want to find out magnetic field at any point P, which is in the region outside the capacitor, so we consider any point P and this is outside the capacitor. So then in order to calculate the magnetic field B at this point P, and we want to calculate the magnetic field B at point P. So if we want to calculate the magnetic field at point P, then we have to use the Ampere's circuital law. And for this, we have to take the line integration of the magnetic field over a closed surface. So to take a closed surface, we consider a plane circular loop whose radius is small r and whose direction is perpendicular to the direction of current carrying wire. So this is our current carrying wire. So for example, say here we consider any circular loop which is perpendicular to the direction of current carrying wire, and this is a circular loop of radius small r and whose center is symmetrical with respect to this current carrying wire. That means it has symmetry on both the sides, so center somewhere will lie at this wire itself. So there is a symmetry, so we can say that the magnetic field B is directed along the circumference of the circular loop. So the direction of B will be along this circular loop, and the magnitude will also be same at each point, because if this is a current carrying wire, if we zoom this area, say this is our current carrying wire and this is a circular loop we are considering, here is the center. So if this is a circular wire, it will have the symmetry at all the points. So at each point the magnetic field will be in the direction of the loop, as well as the magnitude of magnetic field B will be same at each point of the loop. So using Ampere's circuital law, we can simply write down this is B dot dl is equal to mu naught I. So B is the magnetic field and dl, because it's a circular loop, so the circumference is 2 pi r, total length traveled is 2 pi r, and mu naught, and here I is always a function of time. So this is how we can define Ampere's circuital law for this current carrying wire, where the current is a function of time. So this is how we have defined for a circular loop. Now again we can take some other surface, because this is the integral over a closed surface, so we can take another closed surface. So this time we are taking a closed surface of different types. Let us say that we are choosing another surface which has the same boundary that touches the current, but the bottom is between the plates of the capacitor. And the mouth is a circular loop as we have considered in this case, the previous case. So we take another surface shaped in the form of a circular box. So let us say that we draw the second surface. We are drawing with the green color. So here you can say this is a current carrying wire. So here there is a circular loop with the symmetry as the earlier one. And this is another, we take it in a box form, and the bottom of the box is between the plates of the capacitor. So we are taking a closed surface of somewhat this way. Now again, this is a closed surface. We can use the Ampere circuital law. So if we apply this Ampere circuital law in case 2, so we can write down circuital law as B dot dl is equal to mu naught I is a function of time. So B dot dl is equal to mu naught I. So here this B is a magnetic field and dl is 2 pi r. But since no current is passing through the surface, as you can see, through this surface no current is passing. So if no current is passing, then this current should be 0. So we get B into 2 pi r is equal to 0 or B is equal to 0. That means the magnetic field in this case, if we take a closed surface of a circular box form, then in this case the magnetic field is 0. So in this case we get the magnetic field B is equal to 0 because no current passes through the surface. So if we had calculated taking this closed loop, then we are getting B is equal to mu naught I upon 2 pi r, and if we are taking the closed surface as shown in the green color, then we are getting the magnetic field as 0. So here there is a presence of magnetic field, wherever in the second case the magnetic field is 0. So it was concluded that there is something missing, there is some missing term from which we should be getting some magnetic field at point P. So we have to find this missing term so that if we take whatever the closed surface, the value of magnetic field should be same, because in the first case we have taken a circular loop and we are getting a magnetic field, and in the second case we have again taken a circular loop but it is passing through the plates of the capacitor, then we are getting the magnetic field as 0. So these two terms, these two magnetic field we have calculated should be same. So we have to find that term which is missing. So let us proceed, let us find out the term what is missing. So here we have taken a capacitor, so let us go to the capacitor plate. The plates of a parallel plate capacitor. So again we draw a parallel plate capacitor. So this is having the charge plus and this is having the charge minus. So these are the two plates of a parallel plate capacitor. Let us say that each plate is having the area capital A and total charge Q. So if we calculate the electric field E between the plates of the parallel plate capacitor, then we know the formula, the flux phi is equal to E dot A. So the electric field is Q upon epsilon naught A, and this is multiplied with A. So this is equal to Q upon epsilon naught. Now the current we are taking here is a function of time. So we can simply write down I is equal to dq upon dt because the current is a flow of charge with respect to time. So if we differentiate this flux phi, electric flux phi, with respect to time, then d phi E upon dt will be equal to d by dt of q upon epsilon naught. So this epsilon naught is the permittivity of the free space. So this is a constant and this will be dq upon dt. So from here we get dq upon dt is equal to epsilon naught d phi E upon dt. And what is dq upon dt? dq upon dt should be the current. So this term epsilon naught d phi E upon dt also represents the current. So we can say that this is the missing term in the Ampere circuital law. So now we can add this term onto the Ampere circuital law. So our Ampere circuital law is B dot dl is equal to mu naught I, which is a function of t. Now we can add this term because this is also the current term. So this is our current due to the conductor, and this is our current which we call as displacement current. So we can write down Ampere circuital law as B dot dl is equal to mu naught. This is the current due to a conductor, and this is our displacement current. So this term epsilon naught d phi E upon dt is called as the displacement current. So that means in the first case, if we are taking our circular loop outside the capacitor, so here we are having only the wire. So we have only conduction current. Here the current is flowing like this. So this is due to conduction. So here the current is only conduction current. So we get the magnetic field B is equal to mu naught I upon 2 pi r. But when we take this loop in this form, that this is between the plates of the parallel plate capacitor, then there is conduction current here and displacement current here. So we have to take the sum of conduction current as well as displacement current. So that means outside the capacitor place we have only conduction current, that is our I is equal to IC, only conduction current outside the plates of capacitor and between the plates of the capacitor. So the closed loop is in the parameter, it is the sum of conduction current as well as the displacement current. So if we take the second loop, then our current I is the sum of conduction current as well as displacement current. Now let us go to the physics of displacement current, how this displacement current is produced. This is the circuit we have used to study the Ampere circuital law. So here you are using any voltage source and here the current is flowing through. Here we are taking a parallel plate capacitor. This is the positive voltage and this is the negative voltage. So we can consider this plate as to be positive, having the positive charge, and this will be having the negative charge. So the current I is flowing through here and also the current is throughout here. So if you want to calculate the Ampere circuital law here, then we have to take a closed loop. So we can take closed loop. We can take this closed loop anywhere, like we have taken it here. Similarly, we can take it here or here or here. So anywhere our Ampere circuital law is valid, because in this loop, this loop, this loop or this loop, the current is flowing because we are using a conduction wire. So whatever is the current flowing is the conduction current, and we can simply write down that B dot dl is equal to mu naught I. This I is the conduction current which is flowing in this conducting wires and which is varying with time. So anywhere in this conducting wires, this Ampere circuital law is holding true. But if we come to the region between the plates of the parallel plate capacitor, then there is no conducting wire. So we cannot take the conduction current here. Now if we want to check if there is really some electric current there or not. So how can we check the electric current? Because if there is varying electric current, if there is changing electric current which is varying with time, then it will obviously produce magnetic field. Simple physics that the changing electric field produces magnetic field. So here the current is changing, magnetic field should be there, here it should be there because the current is varying, current is varying, current is varying. Everywhere the current is varying, so the magnetic field should be present. But what about the area between the plates of the capacitor? So let us check that if there is some varying electric field or not. Because if the current is present, then there should be some varying electric field which will be creating the magnetic field. Now in order to find out the magnetic field, we can simply use a magnetic compass. So say we use any of the magnetic compass anywhere within the circuit near to the conduction wire. We can put it here or anywhere of your choice you can take where you can put this magnetic compass. So if you put it here, then there is a changing electric field due to the flow of current, then it will show some deflection, that is the presence of magnetic field. Here also it will show some deflection, here it will show some deflection, the presence of magnetic field. Here it will show some deflection, here also it will show some deflection. But the interesting thing is that when we keep our magnetic compass here between the plates of this capacitor, then also it shows some deflection. Then this is something interesting, that why it is showing some deflection. If it is showing some deflection, that means there is magnetic field is present. And if the magnetic field is present, it indicates that there should be some changing or varying electric field. That means between the plates of the parallel plate capacitors, some changing electric field is present here. That means some electric field is transferring from here to here. So this is a varying electric field, and this varying electric field is in turn generating this magnetic field. That is why our magnetic compass is showing the deflection. So if it is showing the deflection, there is some electric field, and electric field shows that there is some movement of charges here, and there is a flow of current. So there is no conduction wire here. So if there is some electric field, that means there is flow of some charges, and if there is some flow of charges, then this flow of charges we should call as current. So if electric field is present, that means some current should also be present here. And this is due to the flow of charge. And this current, there is no conduction wire, so this current we cannot call as conduction current. This is simply due to the transfer or due to the displacement of charges. So this current is generated due to this displacement of charges. So we call this current as displacement current, which is present between the plates of the parallel plate capacitor. So wherever you are taking a circuit, so anywhere you can use Ampere's circuital law, and Ampere's circuital law is B dot dl is equal to mu naught I, where I is the current which is flowing. So if you take any of the area where there is conduction current, then this conduction current will give us the equation of B dot dl is equal to mu naught I conduction current. But here between the plates of the parallel capacitor, there is no conduction current. But that doesn't mean that our magnetic field is zero. Experimentally, we observe the magnetic field, so there should be some magnetic field. And if there is no conduction current, then which current is present here? The current which is present here is the displacement current. So if we add this term of displacement current here, then our equations become complete. That means either the conduction current is there or the displacement current is there, and that will give us the total magnetic field. So this is the physical significance of the displacement current. So now we know easily what is the displacement current, and we have also derived a mathematical expression for it. Hope it is very much clear to you in the simplest form. If it is clear to you, please comment yes in the comment box.